Okay, now we're on our last substantive video. This should be video 7. I believe I've got them numbered correctly. All right. And what we're going to talk about is alternative methods for dealing with multicollinearity. So I began with all of these assumptions, and one of the assumptions last week that we talked about was no perfect multicollinearity, and then we talked this week about what are all the problems with multicollinearity, and we realized that it really affects hypothesis testing much more than anything else. However, as we delve into some parameter estimation and partitioning of why, we see that multicollinearity really does screw things up in regression fairly good. And it's not enough to just say multicollinearity is a problem. It's probably better for us to think about alternative solutions for dealing with multicollinearity. So I want to go through a few options. So first, we can delete variables or predictors from our model. Now, that makes perfect sense, particularly when they're redundant, or if they can be justified that one variable probably accounts for everything that the other variable does and more. And you always want to keep that variable that has the and more part of it. But oftentimes we have correlations among our predictors that do not allow us to just select one variable over another for theoretical reasons, and certainly not for just empirical reasons. We want to have good justification for selecting our variables and potentially for deleting any predictors that we have. Now, on the positive side of deleting predictors is that we want a more parsimonious model. And remember, as we were looking at all of the tests and penalizing functions, every single one of them penalized us when we had greater number of predictors in our model. So our first step of dealing with multicollinearity benefits us, but it's oftentimes not terribly practical. A second method for treating multicollinearity is we can combine collinear predictors, or any predictor that's really highly correlated, we can combine them. Now, there are different ways of combining them, so I'm going to show you the simplest way. What we do is we standardize each of the variables, and then we just take the mean of them. And that's just the R code here. So if you standardize two of your predictors that you know are highly collinear, here it's x1 and x2, and then what I can do is I can just run my model, and now I only have one predictor, that's x1 and x2z. I put z in there just to note that they are indeed standardized, and that's the mean of x1 and x2. And if they're highly correlated, what I get is a more parsimonious model, because now I have one predictor as opposed to two. So I have x1, x2, z as opposed to x1 and x2. So that's good, but also I might be throwing away some common variance or unique variance in the x1 and x2 that would really help things out. So combining collinear predictors, this is a brute force way of doing it, and I'm going to talk about another combination in a little bit. Third approach is to use alternative regression procedures. And there is one, ridge regression, and in particular ridge regression is useful. It's useful when you have multicollinearity, but there are a lot of downsides to it. And instead of going into too much detail, the only thing I want to say is that first, ridge regression is probably not available in all stats packages. And two is ridge regression oftentimes leads to parameter estimates and hypothesis tests that are very difficult to interpret, and certainly difficult to publish in an area where ridge regression wouldn't be a common tool. So I'm not going to go over that too much. There's plenty to read about it if you're interested. Highly recommend that for those of you who encounter really sticky problems with multicollinearity, you might want to just consult some first primary sources on ridge regression. The next two procedures are really much more prevalent in psychology and social and behavioral sciences and even medicine. The first one is to reduce predictors, but reducing them, instead of combining them, doing a mean computation on z-scores. Instead, what we can do is we can calculate principal components And the beauty of principal components is, as many of you have learned, however many variables you put into a principal component model, you will get the same number of principal components back. But the nice part about those principal components is, by definition, they are unique. They have correlations among the principal components equal to 0. And so therefore, if I put two variables in and I extract two principal components out of that, I will have two principal components that have a correlation of 0. And here, I've run a PCA, and when I run my PCA, now I have two principal components. I didn't name them anything fancy at all. I just selected the columns. And now you can see the first principal component is a linear combination of my two variables, x1 and x2. And this linear combination is the first principal component is the one that captures the majority of the variance from those two variables, so that that principal component has the maximum amount of variance possible. Principal component 2, therefore, has whatever residual variance available from the two variables once that first principal component has been partialed out. So what does this mean? It means that the first principal component has probably a lot of x1, x2 stuff in it, variance in other words. The second principal component has unique variance and variability that doesn't really account for a whole lot in y. And you can see that from our results. Now, why is principal components a little bit, perhaps a more efficient combination of our collinear predictors? Well, in our first one, we combined both of our x1 and x2 together, and we took a mean of the z-scores, and then we only had one single predictor. Well, if there was a unique variance that was not accounted for by that mean for either x1 or x2, that would be omitted. And so therefore we might actually restrict how much variance in y we can account for. But if you look up here, this is how much variance we accounted for. If you look at our multiple r squared, we have 35%. If you come down here, you see we have the same 35%. Now, the only difference is this is our adjusted r squared. Remember, that's going to penalize us for the number of predictors. So this is 0.33, 0.34 we'll call it. And if you come up here, this is 0.34, but it's a little bit higher. And it's because we only have a single predictor here and we have two predictors down here. So there's always a trade-off. So PCA is a unique solution for reducing multicollinearity. Finally, or actually there's two others, but the fifth one is probably much more relevant to most of your interests and something that you should seriously consider. And that is centering your variables. Now, centering, you can center your variables by standardizing them without question, but this centering is just mean centering them. And it's a little bit different because all we're going to do is we're going to take each of our individual values and subtract the mean out. And you know that this is the deviation score when we're calculating the sums of squares. Sums of squares for any single variable is just the individual values minus the mean, and you square that. So sums of squares, this is that deviation score. Now the deviation score is helpful because oftentimes we get spurious relationships among our predictors by having some oddities in our scaling. By mean centering each of our variables, we still maintain the differential variability among our predictors, in this case between our two predictors, but we eliminate any metric that may cause some problems and may increase multicollinearity. So centering variables, you can see here I center my x1, I center my x2, and I center my y. And after I center them, then I just specify my linear model with those centered variables. And when I do that, you'll see I still account for 35% of the variance. It's the same model. The only thing that's changing are my estimates, my parameter estimates, because these are b's, remember, and by By centering them, I'm going to change the metric, so my rise over run values are going to be slightly different, but they're only slightly different. And you'll notice as you go up here, you're going to see very little. You'll see differences in metric, but you'll see very little difference in terms of the hypothesis testing. Finally, creating a logical order and ruling out collinear predictors is something that you can do with an algorithm. There are various algorithms that will enable you to through brute force, assess which set of predictors may actually account for more unique variance in Y, or you can do it theoretically. And this is where the hierarchical partitioning of variance really comes in. As ideally, we want to put our primary predictors in first and give them the first crack at explaining as much variance in Y as possible, and then residualize out the variance and let any other theoretically less relevant variable to take the residual or account for the residual variance in Y. Now that's one approach. An alternative approach might be to allow your competition, a competing theory, to explain as much variance in Y as possible, and that if you have this super new predictor, that you put it in after your competition. And by putting it in after the competition, it's a very risky test. And what you're saying is that your predictor accounts for everything that the previous predictors or the previous models account for and more, and that you're willing to take a hit hierarchically and allow Y to be explained by your alternative, by your competitor. And then by putting in your variable afterwards, or residualizing out the entire model, another model, competing model, and then seeing whether your variable or sets of variables will account for the residual variance. That is a logical order. It's theoretically driven, and sometimes we have two competing theories, and the two competing theories are collinear. And here's a situation in which you can construct a model. It can be theoretically driven, and it deals with multicollinearity because the theory and the order dictates that the first competing theory gets all of the variance that is available first, and then the residual variance goes to your model or to your set of variables or single variables. And that's an alternative for dealing with multicollinearity. And these 6 are generally considered to be probably the more prominent ones. There are alternative methods that we don't have to get into in this class. So I'm going to leave it with this. We will discuss some alternatives later on when we start talking about alternative estimation algorithms. The final video for this week is just the in-class assignment, so stay tuned for that. Be sure to watch it too.